Good morning. Now Bridget has shown you how to do a line of fit by eye, and you've had a little play around with the dynamic geometry software doing that. I'm going to show you how you can more precisely mathematically formulate the very specific line of best fit. So not just a line of fit, the line of best fit. And we're using a method today called the least squares line of best fit. What I have here is a scatter plot. It's created from the Census at Schools data that I was looking at in last lesson. So nothing's changed. It's just not in Excel. It's in a new program, this program called Autograph. We've got along the x-axis, we've got the height in centimetres, and on the y-axis, arm span in centimetres, just like before. Arm span's up here because the y variable, it's dependent on the x variable. We think the height drives the arm span, not the other way around. And the other interesting thing is down here, we're starting our axes at 150 centimetres because we don't want to have a graph with a massive amount of blank space. So we're trying to make sure that the dots take up a reasonable amount of our space. The only other thing that's really interesting is this line at 190 centimetres. I've just put that there as an anchor for some lines I'm going to draw later. It really doesn't have any meaning. I could have put it up at 200 or wherever I wanted. So don't worry about that. So what am I going to do? I've got all this lovely data here and I'm trying to draw this line of best fit that best represents my data. So if I think about it, it kind of makes sense for the very most average point within my data set to lie on that line. So if I think about my heights, my x values, probably the most average value for height I can come up with is my mean of my x values. So we call that x bar. Similarly for my arm spans, y, my most average value for arm span is y bar, the mean of all the arm span values in my data set. So what I'm going to do is into my scatter plot, I'm going to plot the mean. So that's what that green point there is. And I'm going to label it so we know what it is. And you can see that that's been nicely labeled as the mean. And do a little arrow so we can remember where it is. So that's the mean of all the x values is the x coordinate, and the mean of all the y values is the y coordinate. So nothing particularly exciting happening there. Right, so I'm just going to fix that green point on my line. I'm also going to anchor my line to this lovely red line over here. So I've got these 2 points, and what I'm going to do is draw a straight line through them. So now I've got a line. Now we get fun. So what I can do is I can play around with this line to try and come up with my line of best fit, the very best line that represents this scatter plot I've got here. So what am I going to do next? This is where we get a little bit exciting. And the reason I've chosen this software program is what we can do is highlight this line, the green line I've drawn in, which is my movable line that I'm trying to show as my line of potential line of best fit, and my data set. And I'm going to put something called these y on x residuals. You don't really know to know about that. But what I'm doing is I'm showing the distances from all my points to this black line, and the black line is my guesstimate line, so I can move it around. So what I'm trying to do, if I want a line of best fit, I don't really want these giant values here. I've got these big distances of my points from the line, and the same thing if I'm down here. You can see that's not a good line of best fit. We've been just doing that by eye now, putting our lines of fit in, so it's not a good one. So what I want to do is maybe have it something like that. That looks a bit better. But there's just one problem with this method of doing a line of best fit. And if I think about all these distances on the top of the line, we could say that those are positive distances. All these ones underneath the line are probably negative. Certainly they have to be different signs. It doesn't really matter which way you do it. So I've got all these positive distances up here, all these negative distances down below. And what I'm trying to do is to have the best fit line, I'm trying to minimize the total of those distances. But the problem I may have is all these positive values may offset the negative values. And I may end up with that total distance from the line as being 0. Now that really doesn't make sense if you think about it, because what that implies is that all those points sit perfectly on the line. So it's not really a very good measure. We don't really want to. So we've got some positives and some negatives that we're adding together, but we want to try and avoid that offset effect. So the way we've done that in the past is if we square all our values, our negatives become positives and our positives stay positive. So we end up with a much better result. We get rid of all those offsets. So what I'm going to do instead, except it's not quite working, of course, if I click my data set and my line, see if it's going to work. Why does it never work when you want it to? There we go. This time, instead of clicking this little box that says draw lines, I'm going to click draw squares, and you're going to see quite a different image appearing now. So what we've done here, we've still got those vertical distances from each point down to my line, which is, remember, it's my guesstimate line. I can wiggle it around. I've got those distances, but I've turned each one into a square. Now, if you think back to Pythagoras, when we drew out those, the sum of the square of the sides is equal to the square of the hypotenuse, we did exactly that. We drew squares on the sides of the triangles. And this is exactly the same thing here. We're just drawing squares. And what we're saying is, if we have the best fit line, the squares are going to be the smallest. So if we add them all together, the sum of those areas is going to be the least possible value in order for this to be, the least squares line of best fit. So what's very nice is that this lovely technology, when it's behaving, will put in this little lovely equation for me. And what this is doing is it's adding up the areas of all these squares. So we're calling R those distances from our points to the line, and we're squaring them and we're adding them up. You don't really need to know about this, but it's just quite useful, I think. And that's the sum of all these areas for all these olive green squares. And if I move my line around, you can see as I go down here, my squares are getting bigger and the sum of their areas is getting bigger massively when we go down here. So that is definitely not a line of best fit. As we go this way, our areas get smaller. We can see that on the screen, and the sum of those areas gets smaller. So when we have the absolute perfect line, we should be minimizing the sum of our squares. So if we maybe go back to there, I think that's where we're probably at. And what you can do, because it's a very clever software, is put in the true line, and you can see we're so close, because that's my movable line and that's where it should have been. So that is why it's called the least squares line of best fit. Thank you.